Hello everyone! In this video, we will explain how to define and how to export state space models from COMSOL to MATLAB. So let us first explain why this problem is so important. I'm a control engineer, and in order to design controllers, in order to design model-based controllers, I would like to have a state space model of my physical system. On the other hand, other engineers, for example, mechatronics engineers or electrical engineers or some other types of, let's say, chemical engineers, would like to have a model and would like to analyze such a model, or they would like to do a model reduction of such a model. In these scenarios, we would like to have a state space model of a system. So let us illustrate this on an example of plate heating. So let us assume that we have a thin plate, which can be, for example, a wafer in optical lithography machine, or it can be, for example, an optical component such as a mirror. And let us assume that we want to control the temperature of such a plate by using 4 micro heaters. So these are your micro heaters. So we're assuming here that we can exert certain power, for example, based on joule heating. And let us assume that on the back of the plate, we can place thermocouples. So for example, you can place the thermocouples here, 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 and here. However, this is a back plate, so these are thermocouples. So what you can see here on the right-hand side is basically the COMSOL model of such a plate. And I'm going to explain this model in the second part of the video and how to extract the state space model of such a system. Now, for the time being, in order to explain the logics behind extracting the state space model, we need to define inputs and outputs. So what are the inputs and outputs? In this case, inputs are microheaters. So this will be our inputs, and the outputs of the system are thermocouples. So our system has the following representation. This is your system. We have inputs. We will denote them by U, and the outputs are Y. So the outputs of the systems are some internal variables inside of the system that we can observe or that we are interested to observe. Inputs are external actions that we use to control the state of the system, to control some parameters inside of the system, for example, to control the temperature in this case. Now, our goal is to model such a system and to extract a state space model. So the state space model of such a system will have the following form. Where? Here. E, A, B, and C are the matrices. X is the state vector. U is the control input vector. And Y is the output vector. Basically, the state vector X consists of temperatures at the discretization points. So if you introduce a finite element mesh over here, I'm not going to sketch the whole mesh, but only some part of it. The state of the system are the temperatures at the discretization points. Output vector consists of 4 entries, where every entry is basically the temperature observed at a certain predefined point, that is observed by thermocouples. Input vector U consists of 4 components in our case, where every component corresponds to power exerted by a microheater. So the state space model of the system relates control inputs, that is power exerted by microheaters, and control outputs are observations by thermocouples. So what you can see over here is the state space model, and you can see the sparsity pattern of your matrix E. Usually, COMSOL Multiphysics permutes the entries of such a matrix such that it has a banded form or band form. So our goal is to extract these matrices. We want to extract E, A, B, and C matrices. And once we have our state space model, we can do a number of things with such a model. First of all, we can design observers and model-based controllers. For example, we can design a Kalman filter, or we can design an LQ linear quadratic controller. Also, we can do model reduction, and there's so many possibilities. And also we can play with stability. We can analyze actually the stability of such a system. So, how to extract such a model? Well, in order to extract such a model, we have to understand how COMSOL models inputs and outputs. In our case, or in any case, to be more general, inputs are modeled as parameters. So we're going to define in our COMSOL model parameters. And these parameters will correspond to inputs. The outputs will be defined by COMSOL probes. So we will use COMSOL probes to define the system outputs. Okay, so let us first define our plate, and let us define inputs and outputs. So we start with the model wizard. We click on 3D, then we click on heat transfer in solids, we click on add, then we click on study, and we click on time dependent. Since we are considering state space model, we are talking about time domain over here, and we click on done. So here's our main window. Now we have to follow a few steps over here. First, we're going to define the geometry. Right click on geometry, we click on cylinder. And here's the cylinder menu. We're going to define a cylinder with a height of 0.2, center at 0, 0, 0, and we click on build select. So here is our cylinder. Okay, now let us define points at which we're going to place actuators and sensors. That is, the points at which we're going to place thermocouples and heaters. To do so, basically, we'll click on geometry, we'll click on more primitives, and we'll click on point. Okay, here's our point. So we're going to call this point observation point 1. And we're going to place the first thermocouple at the position 0.3, 0.3, and 0. That is, we're going to place it on a back surface. We click on build select. So here is our point on the back surface. Now let us duplicate these points. We click on right click, and we click on duplicate. And let us repeat this. Now we have 4 points. So this will be observation point 2, this will be observation point 3, and this will be the observation point 4. The coordinates will be minus over here, here minus, and here we'll have minus and minus. And we click on build select. Here are 4 points. The next step is to define the regions at which microheaters are acting. Now, we can model microheaters as points, or we can model them as regions. If we model them as points, we will most likely end up with certain singularities in our model. The better option is to model heaters as basically as regions. So we are going to define a region, for example, a circle, and we are going to assume that at that surface or at that circle, we will have certain power acting on. To do so, we will need to define the work plane. So we right click and we click on work plane. Good. Here's our work plane. And we're going to offset such a work plane for the thickness of our cylinder, and we click on build select. So here's our work plane. And here on that work plane, we are going to define 4 small circles. So this is our first circle. We're going to call it actuator 1. Now, its position is going to be 0.5, 0.5, and the radius is going to be a small radius, let's say 0.02. Or let us increase this a little bit, 0.04. So here is our circle. So we're going to assume that thermocouples, sorry, not the thermocouples, we're going to assume that basically microheaters are acting on this surface. Let us repeat this procedure for the remaining 3 microheaters. Good. So here are our 4 heaters. Now, here it's very important to specify how these regions are modeled in 3D. So if we click on here, resulting object selection, we're going to select domain selection. So in 3D, once we return to 3D, these circles will be represented as domains. And repeat this for other 3 circles. Okay. So if we go back and we click on build all objects, here are our microheaters. And you can see if you can see that if you hover over the circle, you can basically see that COMSOL recognize it as a region. The next step is to define the outputs and the inputs. That is, we need to define the parameters and the probes. To define the outputs, we are going to use the probes. So we click on probes and we select the main point probe, since we are assuming that thermocouples are used as probes. So we click on the main point probe. Now, we want to assign the probe to one of these points on the back surface, on these observation point 2, observation point 3. So how to do that? Well, we can manually enter here the values, right? We can do that. However, there is another trick that we can use. So Under the menu geometry, there's an option to measure. So we're going to use that option. Before that, we're going to click on this icon here such that we can see the points. And we can basically zoom in, click on measure, and click on the point. And you can see over here that approximately the probe is assigned to that point. Okay, so let us repeat this procedure for the remaining 3 probes. There are some inaccuracies here, but we can correct for these inaccuracies. Good. Now we have assigned a thermocouple to the observation points 1, 2, 3, and 4. The next step is to define the control inputs. So we click on parameter and we click on name and write down control 1. And we set the value. We're going to set the value of, let's say, 50 watts. And we repeat this for control input 2. We set the expression. And control 3 and control 4. The next step is to assign the boundary heat fluxes and to relate boundary heat fluxes with control 1, control 2, control 3, and control 4. To do so, we click on heat transfer in solids and we click on heat flux. Now, here we first need to select basically our domains, right? So, heat flux 1 will be acting on this surface. So we click on this region over here. And we're assuming basically under the option we can have 3 options. We're going to assume a fixed heat rate, and here we're going to enter the parameter control 1. So in this section we're going to write control 1. Okay, so by doing so we have assigned a control 1 with 50 watts of power acting on this region over here. So let us repeat this. Okay, so let us do this for heat flux 2. Here we're going to raise. Here's control 2. This will be third one. And this will be the last one, the fourth one. Good. Let us see control 1, control 2, control 3, and control 4. Okay, here we have an error. We should erase this. We should select the region. Good. So let us repeat control 1, 2, 3, 4. Perfect. Let us now define boundary initial conditions. So we click on heat transfer in solid. We are going to assume basically surface to ambient radiation, and we're going to assume basically a temperature of 273 Kelvin. This is the ambient temperature. Now, notice by basically clicking on this option and selecting the surface to ambient radiation, we are actually introducing model nonlinearity, since the radiation scales with 4th power of the temperature. However, our model that we're going to export to MATLAB will be linearized model, and we are going to specify the linearization point later on. Let us specify initial values. So we are going to assume an initial value of 273 Kelvin. Okay, and let us go over other options. So we have thermal insulation on certain areas. So let us assume it's on the back, 4th, right? Here we didn't actually assign surface to ambient radiation, right? That's why everything is thermally insulated over here. So we're going to assume basically that on this surface, we have surface to ambient radiation, and basically thermal insulation is going to only be over the border of our cylinder, and it's some other points such as 7 and 8, 1 and 2. These are actually points 1 and 2 and 7 and 8 correspond to the edges, as you can see over here. Okay, so now that we have defined boundary condition, initial conditions, we need to define material. So we're going to basically click on material, right click, add material from the library, and then we're going to click on aluminum. Actually, it's aluminum alloy. So we double click aluminum alloy. So here is our aluminum alloy, right? Domain, actually not the domain, yes. Domain 1 means made of aluminum. And here we're going to just, in the radiation section, we're going to use user-defined emissivity. So we're going to click 0.5. Now, the final step actually is to adjust the time interval. Now, since we are talking here about the heat conduction process and radiation, the time constants are very slow. So if you would just leave time like this and if you would solve the problem, you will obtain the temperature doesn't change. You need to increase the time. So we are going to increase the final time. We're going to set it to 3000 seconds. And we're going to click here and we're going to put 100. What is 100? 100 means that every 100 seconds we're going to obtain a snapshot of our temperature. Okay, so let's click on the mesh. If you click on now, here's the problem. Since I dropped my microphone, we need to adjust this. Okay, not minutes, we're going to put here seconds, and this should be okay now. And we're going to click on the mesh, and we're going to click build all. So here is our mesh. This is too narrow, too small. This mesh is, we're going to use a little bit coarser mesh, or even more coarser, since the size of your state space model will be directly proportional to the mesh size. Okay, so we have defined geometry, we have defined inputs and outputs, we have defined the material, boundary heat sources, adjust the time, and the next step is to solve the model. So if we click on compute, we are going to obtain the solution. Now, having a computer with 16 gigabytes of RAM, and yeah, you can see here in few seconds we obtained the solution. So this is our solution. This is the final graph, or the first graph that you have seen at the beginning of this video. And here you can basically see the isothermal contours. And what is interesting, COMSOL automatically provides temperature graph. So this is how your temperature behaves in time. We can play with the parameters. We can adjust here the parameters. Instead of, let's say, 50, we're going to put 100. And let's see what happens. And we click on study, and we click on compute. Interesting how you can see over here in real time how your system behaves. Good. So here is our solution. You see the temperature increases. Now, here comes the main part of this video. Our goal is to export such a model to MATLAB. Now, before we do so, it's always good to click on compact history. By doing so, in the MATLAB file that we will generate, the expressions will be compressed right now. And as I explained in one of my previous videos, we are going to save the model as a MATLAB file. So we're going to click on Save As, and here you can select a MATLAB file, model file, right? And we're going to call it Model 1. Okay. See my previous video. Also, a link to this video is given in the description below for more details on how to export, not to how to export, more details on how to actually code everything from MATLAB. So you can use MATLAB to code everything. So let us go to MATLAB. Let us open the model. We click on Open, and here's our Model 1. So this is what you get. This is our model. Okay, we are not going to use it as a function. We're just going to raise here, and we're going to raise end. Now, here is how basically COMSOL models the system. This is used to create geometry. Here are the code lines that are used to define control input. So you can see control input 1, control input 2, control input 3 to 4. We can adjust here the parameters manually, right? And I'm not going to go over all the details. What is important for us is this part over here, and the parts on probes. So let us see how COMSOL models probes. So we click on Find, we we search for probe. So here are probes. This part corresponds to probes. Now, this is where we assign. So these code lines over here are used to assign the probes to certain points. You can clearly see these lines, right? So we can do reverse engineering. So we can actually figure out how COMSOL models everything, and we can play with the parameters. And from my perspective, MATLAB is a more powerful, actually using COMSOL Multiphysics from MATLAB is more powerful than using the graphics user interface. Now, we can clearly see here that these are the inputs, and the probes are called PPB1 to 4. So these are the probes. Why this is important? Well, this is important since we are going to basically use these names to extract the model. Now, I'm just going to paste what I wrote in my previous code. So I'm going to copy and paste these code lines, and I'm going to explain what is happening over here. So with this single line of code, you're going to extract your model. Okay, the function is mph state. And we have basically, you can look into the COMSOL Multiphysics or live link tutorial, and you can read more about this function. Now, we specified the model. Model is the internal name that COMSOL uses. Solution 1 is one of the solutions we are actually using. So you need to compute a solution before you call this function. Out is what you want to extract. In this case, MC is basically your your state space model looks like this. MA plus X plus MB times input, and you have YCX plus DU. You don't have basically the direct feed forward matrix, since system doesn't have, since basically you have delays between control inputs and outputs. This is going to be 0, right? Now, input, here you define the inputs, and you'd use basically, I think this is a dictionary in MATLAB. You specify 4 strings. Actually, you specify the 4 parameters: input 1, input 2, input 3, and input 4. And then finally, you specify the outputs. Here are outputs. They are domain, not domain, they are the point probes. Here are point probes: 1, 2, 3, and 4. Now, you need to specify here the option sparse on, since this model is large dimensional. The matrices can have easily million by million, and you cannot store this in a computer memory. Even if you have a supercomputer with terabytes of RAM, it's still difficult. And here you can play with the parameters, initial solution, where do you linearize, and etc. Now, let us call this, let us just execute these lines of code. Okay, now what is happening here is basically you're calling internal COMSOL functions, you're defining the model, you're solving the model, and then finally here you're going to extract the model parameters. And we have to wait a little bit. Probably it's going to take about the same time as in the case of the COMSOL model. Great. So we have executed, we have extracted the model. Now, with this code line, I'm going to basically extract these matrices. Now, and I'm going to do SPI EM. I want to see the sparsity pattern of your EM matrix. So here is the sparsity pattern of our EM matrix. Here is our sparsity pattern. So it's a banded matrix. We can do SPI AM. This is our A matrix. Sparsity pattern. We can do sparsity pattern of CM matrix. You can clearly see that this matrix is a fat matrix, since we only have 4 outputs and state order is 9,000 whatever, and we can do SPI's BM. This is your BM matrix. It's a tall matrix, only having a single, actually we're having 4 inputs, and state dimension is 9,000. Good. In my next video, I'm going to explain how to discretize such a model, such a state space model, and how to simulate such a discretized state space model, and how to compare the response of such a model with the response computed using the COMSOL graphic user interface. This will be the final validation of the model extraction approach. Here we should emphasize that this model is a linearized model, since you're here selecting a linearization point. There's another option how to do this. You can also look into the help for the MPH state function. Okay, I hope that you enjoyed this video, and stay tuned for more videos. Have a nice day. Bye.